And today let's talk about something you definitely haven't heard regarding quantum entanglement. As before, my name is Yuri Trifonov, and today we're going to dig into, let's say, the aspects of this complicated damn long-range effect, and try to figure out what quantum entanglement might actually be, and why it is so incredibly fascinating. According to the standard view, quantum entanglement is a kind of invisible connection that exists between two entangled, pardon the tautology, particles. This entanglement means that when the quantum state of one of the particles changes, the quantum state of the other particle also changes immediately, so to speak. Quantum states include, for example, the spin of a particle, and in classical physics, such a concept is simply impossible. For something like this to happen, you would need, for example, to literally connect the two particles with a mechanical link. Take, for example, two balls. These two balls can rotate independently of each other. In order for one ball to replicate the position in space of the other ball, either someone has to rotate this ball in exactly the same way, or there must be a mechanical connection between these objects. And these kinds of analogies very often actually ruin the very understanding that we lack when it comes to grasping quantum physics. In quantum entanglement, everything happens more or less like it does with the balls. But as we already remember, in many videos I have told you that not a single particle, at least not a quantum level particle, should ever be compared to mechanical balls. And against this backdrop, it's interesting to look at alternative perspectives on the problem. Usually we start off quite literally from the entanglement of particles. This entanglement either exists from the very beginning, or it is achieved under laboratory conditions, or it happens in some other way. By the way, entanglement itself, the very nature of being entangled, is still not understood. If you ask how this entanglement occurs and what it actually is from a physical point of view, most likely you'll get the answer that these particles act almost like triggers, responding when the state of the other particle changes. In fact, we don't have a mechanism or an understanding of the nature of entanglement. We don't understand what quantum entanglement is, and by today's standards that's actually normal. And because of this, it's doubly interesting to study what I'm about to tell you. Not long ago I came across a rather interesting article, and in this article everything was actually based on something else. The starting point wasn't that particles become entangled with each other, but rather that everything in the universe was already entangled. And the fact that we pick off some fragments of particles, that some particles supposedly start to become entangled with each other, that is actually a reverse effect. We are disentangling them from the rest of the universe, and for a while we make them behave as if they are entangled only with each other. You know what? This version seemed quite authoritative to me and actually seems quite logical. There are plenty of parallels and analogies that can be drawn here. Not to mention ideas like multiverse theories. But even, roughly speaking, in everyday life, you've probably heard the phrase that everything is interconnected. And in fact, if we look at the world around us, we clearly see that everything is interconnected. Just look at the nature around us. I do not know, maybe there is less water, the tall trees have withered, or it started snowing, for example. Any complex process in nature can be viewed as the continuous interaction of one thing with another. The system is so extraordinarily intricate and complex that we are currently simply unable to trace more complicated and branching connections, as opposed to basic linear ones. It is possible that at some point in the future there will be advanced computer systems capable of calculating all this, but for now we can't even predict 2 steps ahead. Because any event, any phenomenon, any process, and any single particle is influenced by an incredibly vast and overwhelming number of factors. And here we can recall various amusing cases, like when cats were introduced to Australia to deal with lizards, but the cats multiplied so much that they started terrorizing the local residents, and now no one knows what to do with the cats. There was a similar story, I think, about llamas or some other harmless animals like that. And it often turned out that what seemed like a simple connection led us to completely unbelievable situations, which sometimes even seem comical. I just realized that this wonderful little model is making quite a noticeable creaking sound, and I'm afraid it might be audible in the video, so let's go ahead and turn it off. But here, probably first and foremost, it's worth discussing how particle entanglement actually occurs. In reality, the laboratory methods for entangling particles are quite complex, and as for entangled particles themselves, if they exist as entangled particles, they generally already appear that way in nature, if you can put it like that. Laboratory methods for entangling particles, in fact, can't really be explained in 5 minutes, but to put it briefly, the first approach is to extract particles from a superconductor, since it is believed that in many cases, superconductivity is precisely due to quantum entangled particles, which interact easily and, let's say, amicably with each other. thereby allowing the conductor's resistance to be eliminated under certain conditions. Or the alternative second method, which of course I am greatly simplifying and condensing for clarity, involves bombarding a special crystal with specific optical properties using a high-powered laser beam. The laser source continuously emits photons with high energy levels. These high energy photons then enter a specifically designed optical medium with which they interact, and once inside they undergo a transformation where they split into correlated pairs of entangled particles or photons with distinctly lower energy levels. And in these cases it seems that entanglement of particles occurs, but now I'm going to tell you something a little different. And I'm going to tell you why the idea to make this video came about in the first place. I was poking around recently and came across an article with a loud headline saying, "Oh, we've achieved quantum communication." As always, it started with all this hype, like, wow, quantum systems can work. The main thing is to say the word quantum as much as possible. If there aren't enough quantum words, then the article isn't real. It's like my academic advisor used to say, I've repeated this many times, that if you hear the word nanotechnology, chances are you've already been deceived. And really, that's true. Nanotechnology used to pop up everywhere. Back then it was trendy, now it's quantum computers that are in vogue, but nanotechnology was mentioned all over the place. So basically, if someone mentioned the word nanotechnology, it meant there was some magnificent, high-level scientific achievement. Well, it's pretty much the same story here with quantum phenomena. So, according to the author of the article, this quantum communication is fundamentally based on the concept that we have entangled particles, which can be physically separated from each other by incredibly vast distances. And as we know, quantum entanglement works so amazingly, there's really no other way to put it, that one particle can be here and the other one can be over there in a neighboring galaxy, and they will instantly, Einstein, they will instantly interact with each other and exchange states. So in fact, according to what is written in this article, it is believed that this phenomenon can be used to transmit information. The underlying logic is actually quite simple. If we have one quantum particle in one place and another particle entangled with it far away, then changing the state of this first particle will inevitably and instantaneously affect the state of the other particle it is entangled with. However, just one but is enough to invalidate everything that was written there. And if you remember, there's this observer effect. I talked about it on the channel. It's quite a complex phenomenon. I recommend finding the video and watching it. I'll leave a link somewhere. So the observer effect is that when a particle is measured, the quantum function collapses from the many states inherent to a quantum particle. Yes, with quantum particles everything is the other way around. The particle, or rather the system, chooses a single, most probable state. And in fact, this is the very act of measurement. In order for the particle we are using, as let's say a means of establishing a connection at the other end of the wire, so to speak, to change its state, we need to measure this particle. Alright, we've measured this particle, and by assigning it a certain state, we want to transmit this information to the other side of the galaxy through quantum entanglement, and do it instantaneously, no less. That would be great. Yes, the particles have flipped somewhere, like a combination lock. Some states have changed, for example, they've changed their spin. For example, we even know that if this particle has a positive spin, then the other will have a negative spin, and so on and so forth. But despite all this, there is one but. In order to understand what state the particle is in on the other end, we need to measure it. Can you guess what will happen if you measure the particle on the other end of the wire? Yes, the state of this particle will also change, and we will never know what the original state was. The only way this strange system could work is if we also have some additional communication channel. That is, we have to send the entangled particle to the other side of the galaxy, then measure the particle here, say what value we got. Since there are pairs of values that alternate with each measurement, we have to communicate this by regular phone, or say by email, or even send a carrier pigeon to the other side of the galaxy. There they will receive this information, take their own measurement, and say, "Oh, it seems to be confirmed." So the problem is that this scheme will only work if there is an additional communication channel that tells us what state our particle is in. And that's something like a wired telephone, like remember in Tom and Jerry, where they had those cans on strings, or maybe you've made those yourself at some point, those children's telephones, childhood pranks. And all of this essentially serves to negate the entire logic. That is why a particle simply cannot just, so to speak, transmit some information about itself. Unless, roughly speaking, it tells us about it itself. However, it is no coincidence that I brought this topic up for discussion right after describing the ways entangled particles are produced within the laboratory setting. There's also an interesting catch here, and I still haven't found the answer to these questions. Maybe I'm confused about something or not fully understanding. The thing is, the method for studying entangled particles is also based on measurements. The laboratory setup used to analyze which particles are entangled and whether they are still entangled with each other is built, let's say, on the basis of mirror reflections. The setup is quite clever, but the logic is basically straightforward and simple. We send out entangled particles. One particle goes straight, the other interacts with a mirror, and then on the detector we need to determine what states these particles were actually in. In my humble opinion, I have a hypothesis that when a particle interacts with a mirror, it changes its state to the opposite one, and thus the particles that we obtained under laboratory conditions and called entangled, we also won't be able to measure. And the logic repeats the very same scheme that we have in this case. The only difference that may exist here is that in the case of this strange connection, which was also described in an equally strange note, it is based on the fact that the particles are separated by a great distance and interact not with a mirror but with certain, let's call them special measuring complexes. But in the case of the experiment to detect entangled particles, the interaction occurs specifically with the mirror. And yeah, I already wrote about this actually on Zen in one of my articles, and right there people started saying that, you see, interaction with a mirror is not really an interaction. But why is interaction with a mirror not considered an interaction? This is exactly the same effect that we see in the observer effect. It is the interaction of a quantum particle with a macroscopic object. And well, in my opinion, in my logic, all these experiments aren't really that precise, to put it mildly. So, my friends, I didn't tell you all this by accident. The thing is, if you analyze the laboratory methods for producing entangled particles, yes, there is some misunderstanding regarding what I mentioned earlier, and it's unclear how to measure this if the measuring devices work more or less like this and are supposed to switch the states of the particles. Alright, let's set that aside and assume that the method works a bit differently than how I imagine it. But despite all that, this method of obtaining a pair of entangled particles is actually quite similar to, let's say, the identification of an object that was already entangled beforehand. Well, my friends, I hope the audio in this video has improved because we now have this truly fantastic piece of equipment that will help us capture and record high quality sound from now on, at least when we are indoors. And in one of the recent videos I was surprised myself at how terribly the sound was recorded when filming indoors, and I decided that something needed to be done about it. Be sure to let me know if the sound has improved with this microphone or if it still sounds bad or maybe it even got worse. That would be helpful, or at the very least interesting. And we also have a Telegram channel that you definitely need to subscribe to using the link in the description. And also, not too long ago, a new feature appeared that I suggest you try out. You can ask me any question related to the project's work, or say about the school curriculum in physics, or about material science, or really anything we've been discussing. You can ask for clarification. Why is this done through a donation form? It's very simple. Otherwise, I might miss some questions. And donations, first of all, help support the project. By the way, you don't have to ask a question, you can simply support the project, and I would be very grateful for that. In fact, this wonderful thing appeared thanks to people asking questions. We've already recorded one video with answers to your questions. I think I'll manage to make a new video soon as well. There are already quite a few rather interesting questions accumulated for that one too. And when you ask a question, be sure to leave some contact information, preferably an email or telegram, so that I can actually reply to you. Recently someone asked a pretty interesting question in the Telegram channel. I think you saw the answer. The thing is, I couldn't reply personally because for some reason the person didn't provide any contact information. But still, thank you for the question, and thanks to everyone who asked such questions. Well then, until next time, I hope it was interesting and useful. Subscribe and hit the like button. Bye everyone.